Hello, class, and welcome to part 4 of section 1.8. This being the intermediate value theorem. So if we suppose that f is continuous on the closed interval a to b, and let capital N be any number between f of a and f of b, where f of a and f and b, where f of a and f of b are not equal, then there exists a number c in our open interval a to b, such that f of c is equal to capital N. So we can kind of see right here a function here in blue. We have a value here of a and f of a. Here's b, and then f of b is all the way up here. There is at some point we have a value c between the open interval of a to b, where f of c is equal to whatever this capital N here is, right? And from this, all that this here means is that there exists at least one of those numbers. We can have multiple, as we do here in this one, where each of these, where it intersects the graph, is equal to that capital N. But the whole point of this being, though, is we have at least one of those. So if we have a continuous function with no holes, we can easily see that the intermediate value theorem then is indeed true. Geometrically, if any horizontal line, y is equal to capital N, is given between y is equal to f of a and y is equal to f of b, then the graph of f can't jump over this line. So it must intersect y is equal to n somewhere, that being whatever this value of c here is in terms of that x-axis. So as an example, we want to show that there is a solution of our equation 4x cubed minus 6x squared plus 3x minus 2 is equal to 0 between the values of a, values between 1 and 2. So for this, we have here from the intermediate value theorem, a here is 1, b is 2, and we want the value of capital N to be 0. So we want a value c to be between 1 and 2, not including 1 or 2, such that f of c is equal to 0. So if we put in the value 1 into our function, we get 4 minus 6 plus 3 minus 2. We get ourselves a value of -1. That's less than 0. If we put in the value of 2, we get 32 minus 24 plus 6 minus 2. And that gives us the value of 12, which is, well, greater than 0. So since this is a polynomial, we know that f is continuous everywhere. And we know that f of 1 is less than 0 and f of 2 is greater than 0. So by this intermediate value theorem, intermediate value theorem, from that, we know that there is a c between the values of 1 and 2 such that f of c is equal to 0. And then finally, we have example 8 here. We want to use the graph to determine the x values for which f is discontinuous. For each x value, we want to determine whether f is continuous from the right, left, or neither. So these particular values would correspond to where we have either those jumps or breaks and whatnot. So that happens at -4, -3, -1, +1, +3, and +4, based upon this graph that I have here. At f of -4, since that's just an open circle, this value here does not exist. So because of that, we're not continuous. For f of -3, down over here, left and right are not continuous. Left and right are not, they're two different values of the limit. So this limit here does not exist. For f of -1, at -1 right here, we have the same phenomenon. The two are not the same, so the limit does not exist. For the value of f of 1, we have ourselves just the left-hand limit. There's no right. So because of that, this one right here also does not exist. Of course, it's an open circle there as well. This is only would be then continuous from the left for this one. For the value of f of 3, again, we have a closed circle here, excuse me, but there's no left hand side, just the right side for this one. So again, this one does not exist, but it is only continuous on the right hand side. And let me just fix my E here. And then finally for f of 4, same idea. Only exists on the right hand side, there's no left hand side. So this does not exist. Again, only continuous on the right hand side. So that's the last little bit here of section 1.8. Do let me know if you have any questions or concerns. Thank you.